today we're going to review how we can apply artificial intelligence to geology and geostatistics. So first, let's take a look at today's agenda. First, we'll give a brief introduction to the new opportunities and challenges in the digital transformation of the mining sector. Next, we'll examine the main concepts associated with machine learning and also artificial intelligence, as well as connecting this to the context of the data we work and how we traditionally carry our workflows in geology. And finally, I'd like to briefly introduce you to that analysis tool used in our company and finish with some use case and conclusions. So let's start understanding the new opportunities and challenges in the digital transformation of the mining sector. So artificial intelligence represents a powerful opportunity for the mining industry. As companies face the ongoing challenge of digital transformation, artificial intelligence is accelerating innovation. This is enable new ways to manage complex geological and operational data, as we haven't seen till this moment. And around the world, we are seeing also how data mining, machine learning, and also big data technologies are reshaping the way we analyze, are reshaping the way we plan and make decisions. So this, of course, opens the door to smarter, faster, and more sustainable mining practices. It's in this context that digitalization has become an opportunity. We know that in recent years, all sectors, not only mine, have faced the challenge of digital transformation, which refers to the integration of technologies such as cloud computing, artificial intelligence, Internet of Things, for mention some of these, that are being applied both in daily operations and across every area of an organization. Moreover, companies have also faced a challenge linked to the lack of the adoption of these technologies, especially considering the complexities of the mining business, from extraction to sales and rehabilitation, and the gap between mining companies that embrace digital transformation and those that ignore it continues to widen. It's evident to my opinion. We make a differentiation from those companies who can survive, can adapt, and those that can actually take these methodologies to lead in the mining sector. So again, over the past 5 years, there has been a turning point in the mining industry, with more and more companies researching or investing in big data, also in data mining and artificial intelligence, to tackle both long-standing and emerging challenges. And it's in this landscape that artificial intelligence and also machine learning techniques are emerging as a key solution to quickly and efficiently extract insights from the vast amounts of data that we work in geology. Okay. Therefore, a predictive approach capable of managing and analyzing data from various sources is essential to deliver actionable results in environments such as production. With this, I want to help improve reliability and operational efficiency in mining operations. So, continuing with digital transformation in mining, the following matrix was developed by Global as a guide for where mining should allocate their investment capital. This in relation to the emerging technologies with a focus on artificial intelligence. This matrix provides recommendation on where to invest in green, where to investigate or explore in yellow, or what areas you, as a company, you need to ignore in red. This, we can see various technological topics across the different stages of the mining process, from prospecting and exploration to mine closure and rehabilitation. And this technological challenge are going to be grouped in 4 categories. The first one, it's the human-artificial intelligence interaction. This refers to the systems in which there is direct interaction between humans and artificial intelligence through a user-friendly interface. In mining, This could involve, for example, augmented reality, glasses to visualize a geological model or an operation in 3 dimensions. Also, the use of cameras and computer vision to alert a worker operating in high risk areas of the mine, for example. We also have decision making that refers to the technologies that support strategic, operational, or also real-time decision making. All this using data science. And also in this topic, we rely on machine learning models. In mining, this includes algorithms that recommend, for example, drill hole placement or also predictive maintenance solutions. We also have the topic for motion that includes technologies involving automatic movement or robotic machinery. This category covers smart robots, autonomous haul trucks, and the use of drones for exploration or topographic surveys. Lastly, we have the pillar of creation that's going to refer to the use of artificial intelligence to generate new information. Here I'm referring to content or models. This typically involves generative artificial intelligence, commonly used in chatbots to produce, for example, text or image based on user prompts. And given all this, I like to emphasize that the opportunity around decision making, as it is recommended for investment across all the stages of the mining process, is a key process, and it's likely due to its relative low barriers to entry, okay? Both in terms in capital and expertise, compared, of course, to the other pillars, to other technologies. Moreover, every decision in mining must be taken with care, as we deal with high capital, high risk projects, and of course, human safety. So again, in this context, having new insights and perspective significantly are going to enhance our decision making in complex scenarios. Although today's session is focused on exploration and resource evaluation, it is important to note that all concepts related to data science, all concepts related to artificial intelligence and machine learning are cross-cutting and applicable to every stage of the mining value chain. So with the context clear, let's look now at the main concepts of data science and machine learning to make the vocabulary more familiar. So artificial intelligence encompasses many subfields, including machine learning, neural networks, deep learning, computer vision, and natural language processing. Artificial intelligence generally refers to the broad concepts that machine can perform tasks intelligently. Machine learning is the idea that machines can learn and adapt through experience. We make the differentiation with neural networks that are very popular nowadays. This is a computing system modeled after the human brain. I'm going to retake this concept later. Deep learning are going to involve large neural networks with many layers of processing units. When we talk about computer vision, we are talking about use pattern recognition and deep learning to understand what is in an image or also in a video. And other topic that is been very popular nowadays is the natural language processing. That is going to enable computers to analyze, understand, and generate human language and also text or speech. So diving a bit deeper into machine learning, I also like to contrast machine learning with simulation. That is also a technique that is very applied to our field. So here machine learning is a subfield of artificial intelligence that are going to enable computers to learn from data and also make predictions without being explicitly programmed. To further explain what that means, let's make this comparison between machine learning and simulation. So simulation is the imitation of a real life process or real life system through a computer model. We use functions to study its behavior or make predictions without interacting directly with the actual system. So typically, when we run a simulation, we start with our initial information about the system. But most important part is that we have a set of rules that are going to describe how the system behaves or interacts. These rules are going to be based on prior understanding of the problem, often in the form of equations or predefined logic, and are used alongside the data to produce results. What happens in machine learning? What is the contrast here? We usually perform what's called prediction, where historical data is going to be used to forecast future outcomes. So in this case, we also start with our initial data, but unlike simulations, we also have the results or outputs. These results correspond to selected variables. We aim to predict those variables or metrics also we want to optimize. Using both the inputs and the outputs, we apply a machine learning algorithm to generate a set of rules that are going to explain the behavior of that system. So then, when new data becomes available, we can use those learned rules to make predictions. So that's the big difference, and that's what I really like to contrast with simulation. That is a tool that we already know in this sector. With all this in mind, we can now take a closer look at the machine learning algorithms available. However, it is always important before using any technique to be clear about the context of the problem. So what kind of problem we want to solve? What does my data are going to look like? With that clear, we can see that within machine learning, we have three main categories: supervised, unsupervised, and reinforcement learning. So starting with supervised learning, it's characterized by the use of labeled data. We use this labeled data to train algorithms and also to obtain the desired outputs. All this is linked to the concept of prediction mentioned earlier, where the labeled data corresponds to the known results, and supervised learning algorithms are going to serve as the rules that model this relationship. Within this group, we have two main categories: classification algorithms. Here, the problem to be solved has a categorical or a qualitative response. For example, the label data could correspond to rock lithology, maybe an alterations, and the goal will be to classify samples based on their based on their geochemical composition. On the other hand, we also have regression algorithms. These are used when the response is a continuous or quantitative variable. An example will be predicting a grade value based on coordinates and also known grade measurements. It's worth noting that the most supervised learning algorithms can be used for both regression and classification problems, as they typically work with numerical inputs, and in the case of classification, they often output the probability of belonging to one category or another. So the other major family is unsupervised learning. In this case, unsupervised learning is going to be characterized by the absence of a response variable. Instead, it is going to focus on analyzing and identifying implicit relationships within the global and local structures of our data. So similar to supervise, we can divide it into two main categories. The first category includes clustering algorithms, which group data based on similarity or dissimilarity. This is a more mathematical concept than a qualitative one. And the goal of these algorithms is to create groups where the elements within each group are going to be as similar as possible, while elements of different groups are clearly distinguishable. So I know that sounds a little bit obvious, but again, we are based the relations of this similarity mostly on distance metrics, and we can think of our data records as vectors to make these similarity metrics. And the second category is going to include dimensionality reduction algorithms, which are going to reduce the number of variables in a data set while preserving underlying data patterns. and also retain most of the information. So these algorithms we also use in data preprocessing. For example, techniques like principal component analysis can reduce, for example, 500 variables down to 10 variables while preserving 99% of the original information. We also have reinforcement learning. It's going to be based on generating a behavior or set of rules in machine learning through what we call rewards and penalties. It's going to be characterized by having an agent that interacts with an environment, adjusting also its behavior or strategy through a series of feedback or signals. If we want an action to be repeated over time, we reward the algorithm for doing so. And if you want the agent to avoid a specific action, we apply a penalty. So these algorithms are especially popular in robotics, also autonomous systems, and we also use them for game simulations. So to give a more practical example, we can imagine that when we train an autonomous truck to drive safely, we're going to use these rewards and penalties. In this case, the environment will be the mine pit, of course, where we could assign a penalty if the truck drives too close to a cliff edge, for example, or in the wrong direction, and a reward if it stays on the designated route and also maintains a steady speed. So finally, we have deep learning, which is going to be characterized by the use of neural networks. These algorithms are going to be often compared or inspired by the architecture of the human brain, where the activation of one neuron or one perceptron can trigger the activation of others. However, the key strength of these algorithms are going to lie in the fact that they consist of multiple nonlinear layers. This means that the functions used in the algorithms cannot be represented as a simple system of equations. Uh, a simple system of equations can be understood as equations that can only use addition or multiplication. Instead, functions like ReLU that are going to use the absolute value, or the functions like sigmoid, which use the exponentials, are going to be employed here. This allows for a wider range of problems to be addressed, as it breaks away from the assumption of linearity. But it also are going to come with a higher computational cost. So again, neural networks fall under the category of supervised learning because training them requires labeled data, and the set of rules is learned through a process known as backpropagation. However, due to the flexibility of this architecture, neural networks have also been successfully used in reinforcement learning applications. So continuing the comparison within simulations that I made earlier, when might it be appropriate to use machine learning instead of simulations? The first case is when the system is unknown. This is mainly associated with situations where we can obtain experimental data, but we do not understand the system very well enough to simulate it accurately. We also have the case when the system is very complex or poorly characterized. Sometimes the system, we cannot understand the relationships, or we lack sufficient initial information to perform simulations. It may also be that the scales make the problem difficult. We may have so much initial information or so many interactions to perform that can difficult to us to have precise results. Simulations may feasible but very, very slow. What happens in cases where it takes a week, for example, or a month to get results of a simulation? It is worth using this methodology to make decisions, or maybe we can apply a machine learning algorithm to first detect patterns and then make predictions. And finally, there is the case where simply we cannot simulate due to the problem context, for example, for image recognition. With all this in mind, We can also ask ourselves in what context we can use machine learning instead of more experiments in mining. It is in this case that we have that experiments or initial information are going to allow us to better understand the systems that we are analyzing. If we talk about exploration and resource evaluation, chemical analysis, drill hole mapping, lithological analysis, also rock quality allow us to understand our deposit and of course reduce the geological uncertainty. But all this analysis consumes a lot of time and are expensive to carry out. So, and even when we obtain all this information, which again, we're working with big data, we are going to generate this large amount of data. All the processing of this data are going to consume resources. So therefore, with machine learning techniques and already having sufficient amount of information obtained through these experiments, we can quickly generate new insights or find trends without the need to further experiments. Okay, so we can leverage this data. However, it must always be kept in mind that machine learning techniques are not a replacement to the experiments, but more an important support for future sample decisions or for the decision-making process. Here, I recommend the book Prediction Machines if you want to learn more about this topic. But in our context, and now with the main concepts of data science and supervised learning reviewed, let's analyze the context associated with the traditional resource evaluation process so that we can relate the concepts for machine learning. So it is important to ask ourselves what type of information do we regularly work as geologists, mine engineers, just a distance. So drill holes generally have associated information about lithologies, also mineralogies, alterations, as well as concentration for different elements, which we're going to use to define economically interesting sectors. Geotechnical information is also important as it indicates, according to rock competence, what the major challenge will be during the pre-feasibility and feasibility studies. But all this information has something in common when we work with geological databases. This is going to be that we're working with georeference variables. This is characterized by having coordinate variables, which indicate the point in space where we're working. Oh, sorry, a pop question. Okay. So we're working with coordinate variables, which are going to indicate where we are in the space. So numerical variables such as concentrations, categorical variables such as lithology and alteration are going to have coordinates x, y, zeta associated. This is not trivial. This is not shared with other industries because we need to consider the spatial correlations within our datasets. In the case of mining, when we talk about georeference data, we generally assume we are working with regionalized variables. When we work with regionalized variables, we assume some hypotheses again, mainly the principle of autocorrelation, which are going to tell us that the distribution of a variable in space or in the region, for example, a copper grade, it is not random and shows some spatial continuity associated to the variables around it. In a way, we can think that there is a set of implicit rules in a deposit that is going to be associated with the geological history of the same deposit. Here, mining engineers and geologists try to express these rules numerically through, for example, variograms, correlograms within other analyses. They are going to be translated into estimation units or volume definitions. For example, the considerations when we are working with these variables, but in traditional methods and when using machine learning, need to have a spatial and physical sense. For example, we cannot have negative grades or lithologies that are not observed in the deposit. Additionally, we will not be interested in samples that are outside the domain or limits of the deposit for predictions. Another consideration is that the data is biased when the information is going to be collected. Generally, we perform preferential sampling when collecting this data, focusing on areas where we expect to see better ore grades. Additionally, when we send drill holes to the lab, we usually only carry out analysis in sectors where there is ore or commodity, which also introduce bias into the information. Another important factor related to this bias is that the vast majority of categorical variables we work with, such as lithology or alteration, are affected by professional subjectivity. We also, here in Latin America, we make this joke of geologists may have different interpretations of the lithology or alteration in the same drill hole segment. So this can be, again, subject to professional subjectivity. Furthermore, the variables, specifically metallic ones, often have very high outlier values. We might have an average gold value of 0.5 grams per ton in the data. This from a deposit, for example, a IUCG deposit. And also very near, we can have samples containing 100 or even more grains per ton. The treatment of these outliers is not present only in the context of geology and geostatistics, but is transversal to all areas that use data science within the company. The main difference lies in the fact that in other contexts, for example, finance, these data are either disregarded or removed for predictive modeling, something we cannot always do or we must handle with caution, since these samples represent an economic benefit. Okay, we have invest time, resources, and of course there's cost associated to each sample. So discard these variables is the last thing we want to do. Another important consideration is that in general, when working with geochemical variables, these are additive variables. So it's necessary to consider not only the data values, but also the volumes associated with them. Finally, there are the effects of the scale or support. It's not the same to work with drilling data in a composite size of 1 meter as it is to work with a composite size of 10 meters, for example. There is a decrease in the number of samples and also in the variation when we increase the size of the composites. It is always important that we are going to use this type of algorithms, compare also or mix machine learning with traditional techniques. We respect the same support size, okay, trying to obtain a better representative on the horizontal axis and also in the vertical axis. So to close this section and moving on to the traditional workflow of exploration and resource estimation, we start with initial information consisting of georeference data. These georeference data are going to come from drill holes as well as our prior geological knowledge. With this information, we first perform a data quality assessment, checking for duplicates, for example, also negative grades between others. Next, we're going to move to an exploratory data analysis. We continue with the detection and treatment of anomalous and outlier values. Then we proceed to compositing and selecting an appropriate support. Next, we're going to perform the clustering of the data to obtain representative statistics. Of course, we want to move to modeling the geological attributes. We're going to validate, for example, with contact analysis, correlation clouds between other techniques. We're going to create these estimation domains. We're going to define them and also their associated relations between them. And up to resource estimation, the major challenge in this workflow are going to be associated with the process. Firstly, the fact that it takes time. We might spend months iteratively going through the different stages until we reach a satisfactory result. But another important aspect is that each step in the workflow are going to require decision making. So it is important to implement any technique or methodology that allows to improve or strengthen our decision making in order to reduce not only time, but also the work involved. So with the concepts of data science and the traditional resource evaluation process clear, let's see how data science can work in geology. And in general, geologists and mining engineers work with data using traditional geostatistical techniques, which have a more well-defined process for data handling. And there are strict standards for data reporting. So what tools do we use? In general, in mining, we use mine planning software, GMP, but they do not have many machine learning or data science tools. Additionally, professionals often work with their own code in Python, also Java or R, which makes sharing more customized workflow a little bit more difficult. Furthermore, there is also an organizational barrier, as our focus is always on production and meeting targets. Sometimes when we are working in the mine, we neglect innovation and do not give the time or resources needed to achieve better results. So innovation is important to remind that innovation always happens at the margins of the mining business. And the good news here is that in recent years, mining has gained momentum in these technologies, and more work is being done in data science, machine learning, and also some neural networks applications. Another important barrier is associated with the fact that the most advanced data science and machine learning techniques are somewhat limited by the need for programming skills and also the knowledge of the corresponding code libraries. So sometimes these machine learning projects are more between the data scientists than the geologists that need to use these tools. So let's take a look at what we use as a complement to this GMP for data science. In this slide, you can see at the top the conventional workflow for data analysis in data science. It includes the collection stage where we integrate information from different sources to move onto the cleaning, where we eliminate incorrect or biased values to avoid error propagation. Not only eliminate, we also treat them. Next, we move on to the exploration stage. We begin to delve deeper into the data. We want to discover explicit and implicit patterns in the information. Next, we're going to move on to modeling, where with a good understanding, we can generate predictive models. And finally, we have implementation or deployment, which is when we use these models to obtain the results. Also, visualizations or conclusions from the information we are studying. All these tasks, when we're working with a typical mine, are not going to be exempt from difficulties. Each one of these stages, the collection of information, the clearing and processing, have an organizational challenge. So most of the time, we have minds that want to work with artificial intelligence, machine learning algorithms. But first, we need to take two steps back and ask ourselves, we have the clear structure to collect this data, to make this data available for these algorithms, right? We want to clean this and process this periodically and fast. And only the collection and the cleaning of this data are going to take around 70 to 80% of the time for a data analysis project. Okay. So next, we will analyze two use cases in our company for generating advanced data science and machine learning workflows for geology. In the first case, we are going to look at measuring the robustness of information provided by drilling campaigns in copper and iron deposits. And the second case involves predicting coal using geophysical information. So again, the first case is related to measuring the robustness of information provided by different drilling campaigns over the time. To give you more context of the problem, in mining, it generally takes on average of 13 years and a half for a new mine to start production and also to generate revenue for a company. For Americans, this statistic is even worse, as it takes nearly 30 years on average to build a new mine. These statistics reflect one of the main problems in mining, associated with the slow pace at which stages and processes are developed, which has been highlighted by the increased demand for minerals in recent years. This raised the following question. Is there a way to transform how we develop projects to substantially reduce the time? And more specifically, how we can reduce project time when we are in the early stages of the mining value chain? Is there a way to shorten the time during this prospecting, the exploration, or maybe the resource evaluation stage? And to answer this question, we proposed the following workflow for drill hole data analysis. We start with a geological database as an input, containing information from different drilling campaigns. In the first step, we are going to load this data and perform exploratory data analysis. Then we're going to carry out the collection, cleaning, and exploration through data visualization to the automation of this process. We want to understand the correlations and key variables for applying machine learning algorithms later in the workflow. In the second step, we are going to compare the available information from drilling campaigns up to a certain point with the arrival of new drilling into the analysis. In this case, we see how our understanding of the deposit are going to change through metrics such as adjust run index or also the global bias. Specifically for adjust run index, we're using geostatistical clustering, which also are going to use machine learning unsupervised machine learning, as we saw earlier. For traditional geostatistical techniques that we want to contrast, we're going to use global bias, which refers to the change in the unclustered mean of this cluster of these groups of data in the deposits. And also we're going to contrast for a more spatial evaluation the variograms and the SWOT plots between different campaigns. With all these metrics, we can assess the robustness of the data in the sense that if the new drill hole information metrics do not change much, it means that they are not providing new or different information from what we already statistically know about the deposit. On the other hand, if the metrics change with the new information, this will alter our global and local understanding of the deposit up to that moment. And when we reach a point of convergence where the metrics do not change much from campaign to campaign, we move to the third step, where we publish a preliminary geological database representative of the deposit so that we can proceed with the other steps of the mining process. We can accelerate the workflow in the mine. this without having to wait for the mesh densification to continue with the subsequent process. So for this workflow, two possible uses were identified when working with iron and copper deposits. The first is associated with iron deposits, is that measuring the robustness and the information provided by the methodology can be used as a support to obtain new perspective for decision making related to drill hole positioning. For example, if a drilling campaign focuses on a specific sector of the deposit indicates through the metrics, of course, that the information from these drill holes is new or different from what is already known, the sector will require more in-depth study. And on the other hand, if the metrics do not change much in that drilling campaign, it may mean that we already have good understanding of that part of the deposit. The other use associated with copper deposits is that we are that the one that I already mentioned, sorry, by having a preliminary database, we can use this information to advance work related to pre-feasibility, also to work with feasibility and mine planning stages, so that when we have final information with the mesh densification according to mining code requirements, we will already have preliminary insights into the challenges associated with this stage, thereby strengthening decision making, which could mean a reduction in time and also in effort. So now for the second case, and to give some context, in this case, a mining company had several coal projects facing the same problem. The time required to extract these drill holes was much shorter than the time associated with obtaining chemical laboratory analysis results, which caused project delays due to waiting times. Furthermore, the chemical analysis sent for testing were expensive and drill holes were not always drilled, so the quality of information was not as good as expected. However, geophysical information associated with the drilling campaigns was available and could be processed in less time and also at a lower cost. This presented the opportunity to use this information to make machine learning predictions, predictions about the location and quality of the coal, using the geophysical data as an input information for the drill hole data outcomes. And for this, our team used data from nearly 40 coal projects that the company had. We were in a big data context. Again, we want to manage oceans of information with these new type of algorithms. And in this case, the focus was also on enabling users to create their own predictive models by selecting the operations and variables they consider relevant for prediction, of course. In certain scenarios, an accuracy nearly 98% was achieved in identifying the presence or absence of coal at a location. The figure here shows the interface process, where we first select the operations to study. We also want to configure and validate the data to be used. Then we're going to proceed with generating and reviewing a predictive model with available information in order to later make predictions with this information. Okay, the main benefit is going to be associated with the fact that predictions allowed us to update geological models before the arrival of laboratory data. With this, we can improve decision making during the waiting times between drilling and lab results. So now, to conclude this section, the first point is going to be that I want to discuss is related to the fact that the barriers to using data science and machine learning algorithms in the context of exploration and resource evaluation are not particularly significant. And what I mean with this is, before this section, you were already data scientists you were already doing cleaning, analysis, and predictions, but specifically within the context of mining and georeference variables. Unlike a traditional data scientist who is more involved in multiple sectors or type of data. I would also like to emphasize the idea that there is a great opportunity for the use of artificial intelligence and machine learning in the mining sector, especially related to decision making. We are in a context where all situations are complex and the actions we take must be conscious, but regarding the basic uncertainty present at every stage and also the risk associated with the sector. And finally, as a more personal appreciation, a more personal conclusion, I believe it is important that as geologists and also mining engineers, we take this knowledge in these disciplines, not only to apply it, but also as a point of comparison of learning, as well as an inspiration to strengthen our understanding of the mining deposits. The understanding of geology, of the geostatistic process. With this, we can expand our range of tools to create more perspective to solve our problems. So thank you very much for your attention. I remain attentive now to your questions. Thank you very much.